Swayam Prabha. Digital India. Educated India.
Welcome everyone to this NPTEL online certification course on techniques of materials characterization. We are in module 9 and we were discussing about X-ray diffraction. So, until now we have discussed about the history of X-ray and then X-ray as an electromagnetic radiation, and also we have discussed about the continuous X-ray spectrum, how it is generated and what are the characteristics of it. And then in the last class we just started with characteristic X-ray radiation, which we will continue in this one, and also we will try to cover a little bit, or we will at least try to start X-ray absorption here. So, concepts, of course, we'll discuss about characteristic X-ray radiation first, then little bit about the production of X-ray, and then X-ray absorption. And in X-ray absorption we will be discussing about mass absorption coefficient and also absorption age. We'll discuss if time permits. So, characteristic X-ray radiation will continue where we ended in the last class. So, we discussed how the characteristic X-ray radiation basically occurs over and above the continuous spectrum when we apply the tube voltage is above certain critical value, and how we are getting K alpha radiation, K beta radiation, etc. at a fixed wavelength. So, this critical excitation voltage Vk, which is basically the voltage necessary to excite K characteristic radiation, and it depends on, again, this voltage strongly depends on the atomic structure or strongly depends on the element itself that is used as a target. But whatever, if we imagine that that target metal is molybdenum and we are working at an excitation voltage above that, or at an excitation voltage for molybdenum which is around 20.01 kilo electron volt, then if we are excitation voltage, that is the tube voltage, if the tube voltage is less than this value, then we will not get any of this characteristic X-ray radiation. That is exactly what is happening here. So, if you look at this, until up to around 20 kV we did not get any of this characteristic X-ray radiation. Only when the tube excitation voltage is increased beyond this value 25 kV, then we are getting. That does not mean that critical excitation voltage is 25 kV. No, critical excitation voltage is slightly above 20 kV. So, 20.01 kV. So, if I can give a critical excitation voltage of say around 20.05 kV, then also I should get K alpha and K beta radiation. It is just that the experiment, with the experimental limitation, the voltage could not be increased, or the voltage rather is only possible to increase at a multiple of 5 kilo electron volt. We could not do it for even less than, for this particular experiment at least. The point is, then the critical excitation voltage, in order to generate the characteristic X-ray radiation, you have to go beyond this critical excitation voltage. Then only we will be seeing in the spectrum, X-ray intensity versus wavelength spectrum, we will be able to see the characteristic X-ray lines, K alpha, K beta and all. So, if we increase it further, the critical excitation voltage, if we increase the tube voltage more than the critical excitation voltage. So, the acceleration voltage for the electrons are now increased beyond critical excitation voltage, then what will happen is the intensity of the characteristic lines, that means the K alpha intensity, K beta intensity, all of them will increase, and that increase, of course, we have also discussed this, that if you increase the tube voltage, the intensity of the continuous spectrum will also increase, and it will be shifting to shorter and shorter. The short wavelength limit will go towards lower and lower wavelength. So, that will continue to happen with the continuous spectrum. So, continuous spectrum will definitely start if you increase the voltage continuously beyond, let us say 25 kV, I increase. Here there is another example is shown for the same molybdenum target up to 35 kilo electron volt. And here you can see the short wavelength is now come down to around less than 0.4, whereas here it is still above 0.4 until up to 25 kV. So this will definitely happen. The continuous short wavelength will start coming in the continuous spectrum, it will be continuously coming at lower and lower wavelength, but the characteristic X-ray will form exactly at the same wavelength. Whether you increase the tube voltage, it will not change. So if you increase the tube voltage from 25 kV to 35 kV, the K alpha line will form exactly at that 0.7, around 0.7 angstrom, and K beta will form exactly around 0.6, whatever we discussed in the last class, within that value. That is not going to change between this tube voltage. What will change is the intensity of this K alpha line with respect to the continuous spectrum. So continuous spectrum intensity will also increase, continuous spectrum minima, the maximum in continuous spectrum will also shift toward smaller and smaller wavelength. All of these things will happen. On top of that, the characteristic X-ray intensity will also increase if we increase the acceleration voltage, and that is what is shown here. You can see that both the K alpha, K beta, both of them now become much more intense when I increase the acceleration voltage to 35 kV, and that if we increase it further, the same thing will happen. This K alpha, K beta, that intensity will keep on increasing, but their position will not increase. So unlike, so this is a major difference between the continuous spectrum and characteristic spectrum. Continuous spectrum, I can change or I can shift the maximum, I can change the short wavelength limit just by changing the tube voltage. But for characteristic X-ray spectrum, I cannot change the position of these characteristic lines. I only can change the intensity of them. Okay. So this is one major change, and that is another reason why these are characteristic, because the way they are generated is basically related to only the atomic structure of the target metal, atomic structure, atomic element, atomic number, only on that. It does not depend on any other things. It does not depend, the wavelength does not depend on anything else. It does not depend on the tube voltage. It only depends on the atomic number or the atomic structure, electronic structure of that particular atom. Okay. Now, the intensity of any characteristic line which is measured, as I said, it is measured over, and if you look at another important point, if you look at this continuous spectrum here, now the short wavelength limit has come to smaller wavelength compared to others, and the maxima also has shifted to even smaller wavelength, and that is even smaller than the characteristic line. So this continuous X-ray spectrum, earlier up to 25 kilovolt, this continuous spectrum, the maxima in the continuous spectrum, so that was at a higher wavelength limit than the characteristic X-ray, but now at a 35 kV, that maxima has gone in the smaller wavelength side of compared to this K alpha. So the intensity of this continuous spectrum and the intensity, maximum intensity of continuous spectrum and the intensity of the characteristic spectrum, these two are also pretty much related, because if you yourself can understand that if the maxima of the continuous spectrum is falling exactly in here, then the intensity of the complete characteristic spectrum will also increase. That is why when we are considering the intensity of the characteristic spectrum, we always make this assumption, or we always make this point, that the intensity above the continuous spectrum. So intensity of the characteristic spectrum above the continuous spectrum, or rather intensity of characteristic spectrum is the total intensity minus the intensity of the continuous spectrum for that particular wavelength. So this is an important point to remember. So this intensity of characteristic line, that is why it is written measured above the continuous spectrum. This depends both on the tube current. Tube current means number of electrons that is hitting. So basically the how many electrons are produced from the cathode, it depends on that, and the amount by which the applied voltage, acceleration voltage, exceeds the critical excitation voltage. That's what. So these two things decide the intensity of the characteristic lines, which is measured above the continuous spectrum, right? Okay. So how it is done? So the number of electrons, if the number of electrons increases, then their intensity, there will be more and more electron available to hit this target metal, and in the process there will be more possibility for generation of K shell vacancy, and that will give rise to K characteristic radiation and so on and so forth. So, the probability of having K shell vacancy will increase. Proportionally, the probability of having or the intensity of K alpha lines will also become higher and higher. So, that is how it depends on the number of electrons impinging on the target metal, and in other words, it will depend on the tube current as well. Again, it also will depend on the acceleration voltage. So, minimum acceleration voltage is needed, that is the critical excitation voltage. If I give anything extra to it, that means the electrons will be much higher or having a much more energy carrying with them. So, they can produce a much more a stronger impact on the target metal and can produce more K shell vacancy, and correspondingly can increase the intensity of the characteristic line. So, this intensity of the characteristic line basically depends on these two things, tube current and the acceleration voltage in excess of critical acceleration, critical excitation voltage. So, if we consider this for the K line, then the intensity of K line again measured above the continuous spectrum, this is expressed as Bi into V minus Vk raised to the power n. B is a proportionality constant and n is another constant, usually the constant value of n is 1.5. Vk is K excitation voltage, the minimum voltage required to produce this K characteristic lines, that is already we discussed, it is around 20.01 kilo electron volt for molybdenum, and the V is the applied voltage. Okay. Now, if we as we were discussing about here, that we have applied 35 kilo electron volt, which is around 15 kilo electron volt higher than the critical excitation voltage of molybdenum. So, then what we can see is the intensity of this characteristic, and intensity you can see it here, the continuous spectrum is below 10, around 7 or 8, whereas the characteristic spectrum is almost above 60. So, counts per second, if we take the intensity as counts per second, so this is around of that. So, it is a relative unit, usually it is expressed as count per second, X-ray photons counts per second. So, this is almost 6 times or even more than, if not 6, even 12 or 15 times than the maximum in the continuous spectrum. So, that is what one point, if we suitably choose this acceleration voltage, we can produce an characteristic K alpha characteristic line, which is way intense than the white radiation, maximum of white intense, and we can make it, in fact, at if an example we can take, that if we use something instead of molybdenum, if we use a copper target and the acceleration voltage is around 30 kV, then the K line, K characteristic line can be 90 times stronger than the wavelength which is immediately adjacent to it in the continuous spectrum. That means the wavelength, if you consider, this is just for moly, but if you consider the similar intensity versus wavelength diagram, if you draw it for, or if you consider it for copper, then the characteristic K alpha radiation, intensity of the characteristic K alpha radiation versus the intensity of any wavelength which is just adjacent to the characteristic radiation, the difference is around 90 times. So, it is a very, very strong and very intense characteristic, very intense signal. Not only it has a very specified wavelength, but also it has a it is very, very intense, or you can make it so intense just by choosing the excitation voltage properly. Another important point is, already we have discussed, that besides being very intense, the characteristic radiations are also very narrow. That means their wavelength is very, very well defined, and there is very little deviation from that particular wavelength, because it is energetically. So, whatever be the randomness in the energy is there, only that much randomness will be reflected in the width of this characteristic X-ray radiation, which is often 0.001 angstrom wide. This when it is measured at half maxima, full width at half maxima, that is almost of that range. So, because of these two properties, that is, it is very, very intense, this characteristic X-ray radiations, and it has a very particular, its wavelength range is also very, very narrow. That is why this X-ray, this characteristic X-ray radiations are best suited for X-ray diffraction experiments. We have discussed about that. That X-ray diffraction experiments means n lambda equals 2d sin theta. Now, d is constant for any material that you are doing. You have the sin theta which you are measuring in the detector, and you need a monochromatic source for diffraction. So that monochromatic, if you have a very monochromatic source, then you can have this entire diffraction condition satisfied for your sample for a particular given sin theta. If it is not a monochromatic source, then d is fixed. You will have a range of sin theta for which the diffraction condition is satisfied. You will be getting and broadening. We have discussed this when we were discussing about the reciprocal lattice and how we are getting a finite spot. Instead of getting a one particular point, we were getting a finite size for the spot. Remember that. So, similar argument here. If you start with a very monochromatic beam, monochromatic means the beam itself with very narrow wavelength, then that will be the best for diffraction experiments. So, that is why the characteristic radiations are used mostly as a diffraction. When we are using it for X-ray diffraction machines, X-ray diffraction systems, only the characteristic radiations are used. Now, that does not mean that we do not have anything to do with the continuous spectrum. Now, continuous spectrum is used when we wanted to have an X-ray image, radiography or X-ray absorption. So, X-ray microcity, when we wanted to have that kind of an imaging, what we need is a continuous X-ray source. Why we will discuss about all of this when we discuss about absorption and so on, but there the white radiation is more important, because there we do not want the diffraction to happen, and the amount of or the energy or this X-ray intensity to we do not want the X-ray intensity to go down because of the this diffraction phenomena, which is another which is an important part of X-ray absorption. So, we do not want diffraction to happen and X-ray intensity to reduced because of that effect. That is why we wanted to have as broad an X-ray wavelength as possible, and we use this white radiation there. We will come to that when we discuss about X-ray absorption. Anyway, now, so let us see on what this characteristic radiation depends. As I said, it depends only on the atomic number. So, basically the characteristic X-ray lines were first discovered by Bragg, W.H. Bragg, and after him this was systematized by another great scientist known as H.G. Moseley. What Moseley told is, he has given basically a law, and this law is connecting the wavelength of a particular characteristic radiation with the atomic number of the target metal which is used. So, basically what it says is, the wavelength of any particular K radiation will decrease as the atomic number of the target metal will increase. So, here it is shown in terms of line frequency. You can imagine that this is inversely, this is 1 by lambda, basically root over 1 by lambda equals C into Z minus alpha. So, that is the Moseley's law what he has given, and this means that the wavelength is inversely related to the atomic number. Okay. So, if we see this is the Moseley's relation which is plotting here. We are plotting the frequency root over frequency versus the atomic number, and for different elements, chromium, iron, copper, moly, tungsten and so on, and for two different characteristic radiation, that is K alpha and L alpha radiation. Okay. Now, this gives us a very important clue, and this is for L alpha. So, tungsten K alpha is having a very low wavelength. So, that means very low wavelength, this one is higher frequency basically, that means a very low wavelength of K alpha radiation for tungsten. So, by the time this one goes to here, it is almost like it is not shown here, but another very important point. So, K alpha radiation, if you want to see for this transitional metal, copper, iron, chromium, etc. So, you will get the K alpha radiation within a reasonable wavelength, okay, the first thing, and molybdenum as well. Also, one more very important point to consider here, that the L lines are not always of long wavelength. That means the L lines are not always of lower energy. Corresponding, we already discussed this, that K lines are usually of higher energy and lower wavelength compared to L lines, but this strongly depends on the atomic number. So, for example, if you consider something like tungsten, the L lines of tungsten has a much it is comparable, the wavelength of L lines for tungsten is comparable to that for K lines of copper. So, that is what it is saying. So, if you consider the K lines around copper, K lines of copper is around 1.5 angstrom, and the L lines of tungsten is also around of that wavelength. So, that is why the L lines of tungsten is almost as energetic, or the energy of the L lines of tungsten is almost the same as copper K lines. That means the energy, ultimately the wavelength and the energy of this characteristic line strongly depends on the atomic number. If we use a heavy element, then that element, for that heavy element, the K lines that will be characteristic lines that we will be getting will always be much more energetic, and correspondingly the wavelength will be much smaller than something like a lighter element compared to that. So, that is what Moseley's law, and this can be explained from the Moseley's law. Okay. So, here we will quickly discuss from all of this discussion that we had still now about continuous spectrum and characteristic radiation. Now, we will be quickly see what is the implication of all of this in the production of X-ray. So, production of X-ray, as we already discussed, is that two ways we can do that, and both involve the whether we use continuous spectrum, whether we use characteristic radiation, whatever, it involves one single thing, that is we need to hit a target metal with highly accelerated electrons. So, in that process, with a rapid deacceleration of electron will produce the continuous spectrum, whereas this electronic transition, K-shell vacancy creation and so on, above a certain acceleration voltage, above this critical excitation voltage, we will be getting characteristic X-ray line. But whatever it is, we need high speed electrons colliding with metal target. So, that is what is the basic working principle of this entire X-ray system, that is called an X-ray tube. Usually that is the name you will be seeing, an X-ray tube or X-ray source. So, this X-ray tube or X-ray source usually contains a source of electron, that is the cathode, a high accelerating voltage, and then a metal target. Okay. And also then obviously there are many more complexities involved in that. Already we discussed that when this electrons hit the metal target, most of the energy of the incoming electrons goes in heat, it converts to heat, and hardly 1% of it converts to X-ray signal. That means the target metal or the entire system for that matter has to be cooled completely. Continuous cooling is needed, and it is almost always water cooled. This particularly this metal target is always water cooled, just so that it does not melt, and that is why refractory metals, heavy elements like tungsten, like moly, they are very good for as a metal target because of their high melting point. One advantage obviously is that they can give a highly energetic continuous X-ray spectrum. The intensity of the continuous X-ray spectrum that these heavy elements they can give is much higher. We already discussed that. Even the characteristic X-ray spectrum that they can give also is pretty high energy, and intensity is very high. So, most often we see, at least for continuous spectrum where the white radiation is needed, we generally tend to see the tungsten or moly as a metal target. If we need characteristic X-ray, then generally we use something like copper, cobalt, moly, and all those. Tungsten is really used for characteristic production of characteristic X-ray radiation, because the acceleration voltage, the critical excitation voltage for tungsten is very high, and it is very difficult to generate that amount, because that is what is shown in the Moseley's law. To generate K alpha radiation of tungsten, it will be very much energetically high, a very high energy is needed, and electron should be accelerated to a very high voltage. So, that is why tungsten is rarely used for when we use the target source. This source we used it for X-ray diffraction experiments. There we tend to use something like cobalt, copper, iron, cobalt, copper, moly, all those materials, all those sources, and where we need continuous spectrum, not the characteristic spectrum, we need continuous spectrum, we tend to use tungsten target. That is what generally is used. Okay. But they are mostly always water cooled. Whatever the source you use, whatever the target you use, almost always they are continuous water cooled. Okay. Now, the X-ray source or X-ray tube contains of course two electrodes, one is cathode and one is anode. The anode is maintained at ground state. Okay. It is grounded and it is almost at the ground potential, the anode, except for a couple of exceptions, we are not going into that. But almost always this anode is kept at ground potential, whereas the cathode is maintained at a very high negative potential, and that is what gives this very high potential difference between the cathode and the anode. Cathode produces the electrons, and under this very negative, they are kept at a negative bias, and under that this acceleration difference, the potential difference between the cathode and anode is kept as grounded. Electrons then gets accelerated and hits this anode material, and generally the negative potential that is given, it depends on what is the target material used, basically what is the critical excitation voltage, how or what above the critical excitation voltage, what is the voltage you want to be. So depending on all of this, the acceleration voltage is chosen. Now this X-ray tubes also can be divided in two types, according to which the electrons are produced, how the cathodes are basically producing the electrons. Number one, it can be gas tubes, in which these electrons are basically produced by ionization of a small quantity of gas, usually residual air in a partly evacuated tube. So this is called gas ionized or gas tubes, where a gas is ionized and an electron flow is created, or the free electrons are created. Or otherwise you can have a filament tube. In that case, it is just like what we discussed for SEM, just like the thermoionic emission, you can generate it. The filament basically works as a cathode and it generates a thermoionic emission, and thermoionic emission will give you this electron as an electron beam, which will then go and hit the anode. So this is basically the way the X-ray is generated. The continuous and characteristic X-ray are generated, and depending on the acceleration voltage and the target metal, you can either generate the same tube. Basically, the way it is done is that if you want to generate a continuous spectrum, you have to use a separate tube. If you want to generate a characteristic spectrum, you have to use a separate tube. It is very much specific, which wavelength, which energy that X-ray source is giving. It is very, very specific. And even within characteristic X-ray, if you want to generate only or want to use characteristic X-ray, then the target metal, you can change it. You can go from copper to cobalt to moly, and each of them comes usually under a sealed tube, and you have to basically change the entire source for getting a different wavelength for the X-ray source. You have to change the entire X-ray tube. Okay. So with this, we close this discussion about X-ray, characteristic X-ray, and we will discuss about the X-ray absorption. We will start it and we will continue in the next class. So when an X-ray encounter any form of matter, part of them are transmitted and part of them are absorbed. And here X-ray encounters means I am talking now in the absorption part, I am talking about a continuous spectrum. I am talking about white radiation. I am not talking about characteristic X-ray. So I am talking just a white radiation X-ray with all possible wavelength. X-ray, just the intensity is important here, not the wavelength of the X-ray signals. Okay. So when an X-ray encounters any form of matter, they are partly transmitted and partly absorbed by the material. And this is what basically is the first observation Röntgen made, and that is why he could use it, or people could use it for radiography, where we have seen that some material, when it passes through the hand, then the flesh and the veins and other, they were not able to absorb the X-ray. So they were basically transparent. X-ray was able to penetrate. They were transmitting the X-ray, whereas the bones, which is much more denser, the bones was able to absorb the X-ray. So on the other side, when you look at here, the X-ray signal is entering with certain intensity, and that intensity is somehow gets lost. On the other hand side, you are getting an modification of intensity, and depending on the density of the material, if you consider that this X-ray beam is hitting different spots here, then depending on the density, which density the material it is encountering, I will have different intensity on this side. Now, if I keep a film on this side, I will be able to generate this kind of an image. That is what is basically the radiographs, or that is what the X-ray imaging is all about. The way this absorption happen, this is basically related to electronic transition to some sense. The only thing to remember is that the electronic transition in atoms, until up to now, we are only discussing the electronic transition because of the interaction of electrons and atom. So, an electron is coming and knocking out some kind of a K-shell vacancy, and then this electronic transition is happening. We are getting characteristic X-ray. Sometimes we get OJ electrons as well, depends on. But all of these cases, we were just discussing or just considering the electrons as the source signal which is causing this vacancy and creating this interaction. So, now in the X-ray absorption part, we have to consider the interaction between the X-ray and material atom. So, that way it is little different from the previous discussion on characteristic X-ray generation, where it was electron material interaction which was giving the characteristic X-ray. Now, what we have to consider or we have to discuss is basically the interaction between X-ray and atoms and how that is leading to X-ray absorption. So, this discussion will continue in the next class. Thank you.